So ladies and gentlemen, I think we can get started. Thank you so much for joining us. I welcome all of you. My name is Armagan Al-Haq. I am the Manager of Program Development and Partnerships at Waterloo Institute for Sustainable Energy at University of Waterloo. And just to share with you, Dr. Jatin Nachwani is my boss. And he is your professor for this course on energy policy. So he is not here, but he has told me to actually be with you guys and take attendance. No, I'm joking. So I would like to welcome our guest speaker for today. Marc Brouillette has been advising provincial and federal government ministries, agencies, and crown corporations for over 20 years on issues in the aerospace, energy, and gaming sectors. He specializes in matters that involve technology-based public-private initiatives in policy-driven, regulated environments. Marc has recently conducted several detailed analysis on Ontario's electricity sector and climate policies. So ladies and gentlemen, please put your hands together for Marc Brouillette.
Well, thank you for having me, and I appreciated Jatin asking me to come and talk about some of the reports that I wrote a year ago. I understand he's fed that into your class, and you guys have already read it, so you're way ahead of me on what I'm about to say. That's what I've been told, right? So I'm just going to get right into it. This work was done from about a year ago, right, in order to inform the long-term energy planning process in Ontario. We're still waiting for that plan to come out that they started it a year or so ago, and that's why the title. A little bit of background on it. This project came about because there were some perceived challenges back in 2016. There were inputs being sought for the long-term energy plan, the LTEP, but there was no data available on emission reduction and the implications on electricity. So there's these two policies that were coming together at the time, the climate file and the electricity file, and it was apparent to most people in the sector that the Ministry of Environment was not really talking clearly with the Ministry of Electricity, or of Energy, I should say, and so there's this gaps of data. So this peer-reviewed study, which I put together and stakeholder round and got people to contribute, it was inspired by Bob Chiarelli, who was the Minister of Energy at the time that we started this effort, and John Godfrey, who was a special advisor to Premier Wynne on the climate file. So I approached a whole bunch of energy system stakeholders, including natural gas, including the local distribution companies, the baseload energy providers, and stakeholders interested in reducing emissions to get ideas on, what are the options that are going forward. The project objectives were to figure out what are the ideas for emission reductions, quantify what that cost would be in order to implement them, how much electricity do you need to actually address them, because there's conversion and fuel switching going on, and then what are the approaches that can be considered for the electricity system design as a whole that would reduce the cost significantly. So that was the objective of the project. So what I'm going to talk about here is an overview on the emission targets, the politics of what was set out a year or so ago, and then we'll look at a couple of examples on buildings, and also throw some transportation ones in there just to describe why this is hard. Talk about the costs, talk about the electricity, and talk about what is the framework under which they're going to decide all this stuff, which when the LTEP comes out, I hear shortly, we'll know what they did with all these ideas. Okay. Can everyone hear me? Yeah? A little louder? Okay. Okay, so the first overview is the emissions challenge. I don't know how many people have, are up on the climate file, but we have legislated the emission reduction targets in Ontario. So the number I focused on is the 37% below 1990 levels by 2030. So when we look at this picture over here, this kind of shows what it means. In 1990, we had this many emissions in the province. This is all CO2 equivalent, so it's mostly carbon dioxide. Had a lot of growth. It came down. We're here today. And then they're expecting it to grow again, and there's a bunch of assumptions, and we have to get down here. So we've got to take out 75 megatons by 2030. Which is that legislated target. So the legislated part, it's important to realize we actually have to do it, because then there'll be issues, right? So under a no climate policy assumption, that's that top blue line. That's what you get, 65 megatons I just explained. And when we start looking at what is the composition of emissions in Ontario, there's three main areas that matter. They're the big pieces of the pie. So we got the buildings being mostly heating. That's mostly what that is. Industry, and then transportation. And transportation splits into cars and trucks, if you will. There's a lot of off-road items in there as well. So there's the challenge that we have to deal with. So the confusion, I mentioned that the climate guys and the energy guys aren't necessarily talking. The Ministry of Finance guys weren't talking with them either. And we came up with this cap and trade notion, and I've labeled it charting a course versus value to taxpayers. Charting a course is important. Someone's got to take leadership. We do have a climate problem. You got to take a step forward. I think it's really good that people are trying to do that stuff. Got to keep an eye on the cost. And why am I talking about this? Auditor General says, well, you're really just putting up a show that's going to allow you to say you did something. And what does that mean? And that came about from the ministry's financial assessment of the cap and trade program. We have to get rid of this many emissions, 18, by 2020. They put the cap and trade program in, and they figure that we'll actually get 3.8 tons of emissions out of the programs that they're contemplating. And then this other 14.9 they're going to have to buy from California. Right? So they've already set up that we're just going to send money out of the province because, right? But they want to get started, right? But that's why these kind of comments come about, is because they're not signing in to actually achieve the changes. And so why? Why would they set this up? Well, the reason is it's really hard and it's really expensive. And when you're a politician, you don't like either of those, right? So but they're still taking leadership, which is important for the province. Okay. Next. This is just a list of all the people that we consulted or whose material we reviewed in order to get ideas. Let's just skip on over that. And we'll get into what does hard mean. So when we start talking about hard, buildings I threw up as an example. For the building sector, we've got the same kind of idea of growing emissions if we don't do anything. And what that means is by 2030, 50% reduction of emissions. And what that means is that 50% of the houses have to lose their emissions, or half the houses have to lose half their emissions, or so on and so forth. There's math around that. And so embedded in this notion of the orange line is they already have built-in efficiency assumptions, because people talk about efficiency improvements, and they also talk about fuel switching, which is get rid of the natural gas. So the built-in efficiency assumption in this growth curve is an 11% building efficiency improvement on energy. I doubled it just because before we started to figure out how much electricity you need, which is another 5%. So we added 50% more than what was projected, using the technologies and the regulations that they contemplate, which left us with a number of emissions that we have to do. So the baseline emissions for 2030, you take out this little bit, which is this much, because this stuff's already embedded in the forecast, right? And then we're left with, we've got to get rid of that much emissions. So to achieve that, we need 50% of the homes need a 33% increase in efficiency, and that's over 10 years. And that's just to get this sliver. Okay, so it's hard, right, to deal with that. And then we're left with those kind of emissions to come out in the end. Okay, at a high level, it's expensive. The price tag I put on it is $27 billion per year. And to put that in perspective, we've had a lot of commotion in Ontario in the last year or so around the cost of electricity. The dollar figure that has caused all that commotion is $3 billion per year. That's the cost that got increased. That's the 25% the government just took out, $3 billion. So this is $27 billion per year. The cost of undertaking climate change by 2030 is not a small number. So we actually want to be kind of smart about it. So how do we frame that up? We've got three different examples. One, if we assume the $27 billion is the total cost, it's coming out of an assumption of $170 per megawatt hour electricity, which is the average price they're expecting for a new generation they'd have to build. And we've got two components, which I'm going to go into a little later. One is the cap and trade proceeds are going to use to offset some cost. And then the users are going to pay whatever the switching costs are that are equal to the carbon price at the time, right? Because this is all around the economics of what does it make when does it make sense to switch? It makes sense to switch when you as a homeowner decide it's cheaper to get the electric option than it is to continue to burn my natural gas furnace. Right? Then you'll switch. And so that can be made economic by a subsidy. So we've illustrated what happens if you get less electricity costs. This is half price, $89, and that will explain where that came from. This yellow thing has to do with how good is the government going to be at spending the proceeds, which will be around $15 billion a year in proceeds out of the cap and trade. So how good can the government be at that? So I've assumed they'll be at a 10% inefficiency. That's this amount. You could argue that they could mess it up and be 30% inefficient by wasting some of the money or spending it in areas that didn't prove out to be like they're a good idea at the time, but then didn't turn out to be helpful. They may choose to use it for other purposes. So if they choose to do that, that'll just rack up the cost. So there's a concern around how effective it's even humanly possible for a government to spend that kind of money. So there's the framework. Okay, so why is it so expensive? And it's because there's a lot that has to happen. So on residential buildings, which I showed that one example, you got to get rid of 50% of the emissions by 2030. So 2030 is not a long time. It's almost only 12 years, right? Commercial buildings, roughly the same amount needs to come out in terms of the percentage. When we get into passenger vehicles, that's an easier problem to solve. Trucks are an extremely difficult problem to solve. And then industry has to get the 35%, which, and a lot of this, what we did with all of this is to get these numbers, we went 37% target, applied it to each one of those areas. Clearly, do more of this, you have to do less of that, so on and so forth by the time frame, okay? Okay, so on heating, just some examples to back up the cost. We looked at a number of different options, but the three big ones is, get just a straight up electricity, use an electric furnace. You can do the air source heat pump, which is more efficient, but a factor of 2. Or you can use a ground source heat pump, which is more efficient again by a factor of 4. Along with this is the costs, the capital costs that go up, but the electricity use goes down. So when we priced out these three different options, to get a new natural gas furnace, so if you consider their old one's dead, they got to buy a new one, it'll cost them this much to buy a new natural gas furnace. Based on projection, the natural gas in 2030, in 2030 it'll cost this much to run this furnace, right? $3,000 a month. The air source heat pump, because it uses less electricity, but it's got more capital, will be around $2,000, and the ground source heat pump will be almost the same as the electrical one, because these things are really expensive. So they make sense on large buildings, and this might make sense in a small apartment, depending on what you're talking about. So to figure out the carbon price, you have to look at the difference of this and the difference in the emissions. But you can see it's not cheap to consider fuel switching, which is why there's a little bit of a topic on that. On automobiles, I stole this slide from Toyota. It's in their annual report. They framed up different options for vehicles. So they got these, the small electric vehicles, which is what's started the EV thing, except for Tesla, which is a full-size guy. The hybrids and the plug-in hybrids for mid-range. There's two dimensions to this. How big is the vehicle and how far do you have to go in terms of distance? And so electric vehicles kind of fit nicely in this domain. Out in this domain, they're talking about fuel cells, like hydrogen fuel cells might be a better option. And there are prototypes of all these kinds of vehicles floating around. And in the middle is these plug-in hybrids. So technology is moving these this way. It is moving those that way. So who knows what's going to happen? But there is a framework for looking at when these make sense, and they all have a role. So we looked at all of them. In terms of transportation, as an example, again, about how hard this problem is, built into the forecast of emission is by 2030, the regulations that are currently planned are to get 26% more fuel efficiency out of the vehicles. So the emission targets the emission forecasts already have this built in. I then doubled that efficiency. Similar with the trucks, they already have a 19% regulatory influence built in, and so we bumped that up by 9%. These are big numbers, right? So you have to have, assuming you're going to get 40%, we've assumed you'll get 40% more efficiency out of passenger cars, we'll get 27% more efficiency out of trucks. After that, we're then starting to figure out what are our fuel supply options going to have to do, right? So the green is the benefit of emission reductions of this little bit of efficiency, and then we have those problems in terms of getting the fuel switching notion in play. Okay, so they're not small targets. So in terms of computing options, this is an example of heavy-duty short-range trucks. We have diesel trucks cost this much. This is the method by which we use to estimate the carbon price. So that's what it costs to run a diesel truck. This little bit is tax. So we're taking that away to look at the base costs, because when they move to electricity, they're going to have to figure out how to recover all of that tax they're getting on gasoline. We're just saying that's a different problem. So regular trucks, diesel, compared to natural gas, almost the same price. Looks like a really cheap option. It's a little bit more. It turns out to be about $53 a ton in CO2 for that sliver of additional cost. And that's because you're not getting rid of very many emissions by shifting to natural gas. Plug-in hybrids, they cost a lot more. They end up with a carbon price around $540. A hydrogen truck will have a carbon price of $582. The reason these are different is this one will get rid of more emissions. Okay? So you have to factor all into play. And the last one is renewable diesel. The problem with natural gas and renewable diesel is even if they converted the entire fleet, don't meet targets. So we need some of those, right? And the problem with renewable diesel is there's not enough feedstock. So you run out of bandwidth. The feedstock being fats and biodegradable bio byproducts. So we kind of have that challenge. So we need to look at that mix in the blend. And what we did is for the electricity assumption, we assumed we maxed this out and filled in with the rest of the stuff. And the reason I mention that is we tried to be conservative on the low end of how much electricity we need. Natural gas, I'll go over this one really quickly. We looked at landfills of different sizes. This is the effective carbon price to take natural gas out of landfills. That's called renewable natural gas. We also looked at natural gas is used to make hydrogen. So there's a carbon price associated with switching natural gas use of hydrogen into electricity use to make hydrogen. And then converting industrial use of natural gas to electricity, we got these different prices. Just to, we looked at those kinds of things as well. So what this curve is the effective carbon price across the bottom and how many emissions we can get rid of. And we had looked at 46 different technologies. Those are all the little blue dots, or all the little dots. And we have this little cost curve that kind of, roughly tells you how many emissions we can get out of the system for a given carbon price. This big carbon price is $800 or $900 a ton. So, we need if you just want carbon pricing, because there's debate out there about should we just do a carbon tax and leave it alone, do nothing else? Will that get us where we need to go? It won't, because you'd have to have it up really high. And you don't need to have it up really high. I'll explain that in a minute. But you can see there's a number of different options. Now, in the analysis we did, we quantified the 46. We have to get to the top. So this is an unknown which we didn't assess. We just assume that magic will happen. We'll get more emissions in proportion to this curve, and to solve those unidentified solutions. Okay? So we've got a mechanism of mapping carbon price to emission reductions. Okay, so the economics on this, in terms of the use of the cap and trade proceeds and the notion I mentioned about you don't actually have to get to an $800 carbon price in order to pay for the to make the decision to fuel switch economic, and that's because you can subsidize. And so we have a model that kind of looked at what happens if the carbon price gets a certain amount. How does that economic decision get played out inside of an individual's brain, whether they should for example switch their home furnace. And we have two different views on looking for that. So when you set a carbon price as an example, $50 a ton, what that means is the user will find it economic to switch to that new technology because its existing fossil fuel fired option will be more expensive. So whenever the effective carbon price to switch is below the carbon price in the market, it will become more economic to just switch, and the user will just pay that cost. It will not need a subsidy. Right? As soon as the cost to switch is higher than the market price, the user will, we assume the user will pay that first portion, and then they'll need a subsidy for the rest. And that subsidy needs to come from the cap and trade proceeds. At $50, that amount would be $5.5 billion. At $50 at 111 megatons, that's the target for 2030. So they have this $5.5 billion, and they can use that to subsidize. And what that means is anything with less than a $230 per ton carbon switching price, they can pay for. Anything above that, they can't. So, to get the math, you need a higher carbon price to shift this up and extend that volume over in order to cover everything. And so we modeled that down here, right? And the example is to get to the 2030 targets, you'll need roughly $133 per ton carbon price, $14 billion per year is the proceeds, and the users will pay another seven to eight, for a total cost of 22.4, assuming electricity at $140 a megawatt hour, which is the average in the province today. Okay, in terms of real cost. So that's kind of how the model works in terms of the two components. Okay, so we set out to look at electricity, and the question is, how much does electricity matter in the fuel switching, in terms of getting rid of the emissions? So when we put all those 45 options that we looked at together, and we looked at the heating, the transport, and the industry, the heating being the buildings, the blue is the electricity. So the electricity figures in greatly into the cost of heating. If you can knock the cost of electricity down, you're going to knock the cost of converting the heating to electricity. Transport too, that blue, and same is more than half the cost, and same with industry. The structure in terms of the blocks is that user pay I mentioned about is this part. The price that requires a subsidy from the cap and trade proceeds would be this, and this is just increasing costs from today because we're trying to illustrate what's going to happen in 2030, and that's made up of the price of natural gas is going to go up, the price of gasoline is going to go up, the price of a variety of things are going to go up, and that's just cost that's going to get absorbed by basically the users. Okay, so but electricity is a big deal. So this brings us to the notion of the electricity. So not all new electricity demand is the same. The biggest thing is that home heating is a winter thing. And so I threw up an example of what's going on in Quebec, because Quebec uses electricity for its home heating. The red thing is, this is Ontario's average energy consumption through the year. The blue is Quebec's. You can see what happens when a province wants to heat itself with electricity. Demand gets really big in the winter. So we need new supplies that will do that. Right? That's the challenge of what we need to have. Specifically in Ontario, the blue is the electricity demand today. The gray is the flat load industrial applications that will just increase base load demand. The orange is electric vehicles and water heating, which kind of go the same all year long. And then the yellow is the forecast need for heat load, assuming ground source heat pumps, air source heat pumps, and electric heating, the mix that we put in. Okay, so big change, right, from today to tomorrow. Okay, how big is that change? There's a couple of perspectives. So the ISO in their planning outlook a year ago came out with a forecast, two scenarios. Well, they had the outlook D, which is their expectation of how much electricity that they said that they're going to need for achieving the emission targets. But they didn't actually analyze it to see if they would achieve emission targets. They just created a scenario that if we did a bunch of stuff, we'd get somewhere, and our analysis says, well, it'll only get halfway to the emission targets. So the environmental commissioner who looked at the stories and the results that came out of the analysis that the Ontario government had done, Outlook D was this yellow line in terms of how many emissions they can get rid of. They got to get down here. That's a gap. That's the same gap that we have over here. There's a lot of confidence that the electricity system is undersized. Since then, speaking with ISO, they've all agreed this is really the curve you need to have if you want to hit the targets. Problem is, the amount of electricity you have to build to hit that target is here, and that's 2030. And there's just no way, it is not humanly possible to build 90 terawatt hours of electricity in 10 years. So we can't do it. Okay? It can't be done. And where does that matter? That matters if you care about cap and trade, because it means we are signed up to buy emission credits from outside the province until we can actually produce enough electricity. So from a policy perspective, we signed up to something very expensive because we legislated the emission targets. Okay, so now we're looking at, well, what are they thinking about? When you look at in terms of our electricity solution. So, and I've labeled it popular politics versus, looking at the generational cost to Ontarians for 20 or 30 years. The popular solution, you hear it in the hype, you've heard it before, right? Lots of hydro imports from Quebec, lots of wind technology being scattered about. Part of the problem is building hydro in Ontario is it can only go way up north. We'll talk about that. And then there's also good ideas around LDCs, but they actually haven't costed that in all the numbers that the government put out. And where does that come into play? If you have to increase the local load for home heating and electric vehicle charging, you've probably heard of that one. In a region, the distribution company's got to upsize its transformers. There's an impact to the physical implementation of the local distribution of that electricity. So we then looked at, is there a different way based on the ideas? And we've got a couple of concepts. One is the wires and pipes integration. That refers to making collaborative use between the natural gas system, that's the pipes, and the wires, which is the electricity system. So how can you optimize hybrid electrical/natural gas solutions to get rid of peaks to minimize the impact on distribution companies? We also looked at distributed energy resources. So to what extent can solar with battery backup serve to increase asset efficiency? So we're going to talk about that. And then the hydrogen economy, which informed a lot by Dr. Fowler in this school, that can do a lot of things with power to gas so that you can use hydrogen as a seasonal battery, which helps with that winter peak load. And then there's low-cost nuclear, which is a big contentious subject, but that was what the findings were. What we discovered, if we're smart about it, that's the label I put on it, is you can have the incremental unit cost of electricity, $89 coming out of here, $170 coming out of there. That's the government's number. The 89 is ours. The carbon price would be $106 instead of $160 per ton. And the biggest kicker is if we do a lot of this stuff smartly, we'll have made in Ontario, exportable industries getting created, and those jobs and all that stuff will actually make the cost of reducing emissions from $27 billion a year, that's the number I started with, down to around $3 billion. So if we're smart about it, we can actually do this climate thing smartly, and it'll be economic boon to the province. So that's the general framework. In looking at why that low electricity cost comes into play, I got two pictures. One is a mock-up of the supply mix that the ISO put out a year ago in terms of what they felt would achieve it. This red line is their forecast of that demand, which has that winter heating in it. All these little spikes, you guys know what those are? Anybody? What are those spikes in the annual supply of electricity? That's the wind, going up and down, being very intermittent, happening all year long. And anything above that red line, can't use, right? That's not usable until they figure out how to use that. The thing that's important is it's a big number compared to that, right? And then these gray stuff, which you can barely see, that's imports from Quebec. Okay, but you have a very messy system. It's very inefficient. The use of wind is only 50% of it can get used, so that means the wind cost is twice the sticker price because you can throw half of it away. When we look at it on the other side and we put, one last thing, there's a 20,000 megawatt additional capacity that's required to solve this problem. On this side of the fence, when we look at those options, if you use hydrogen, that battery storage you mentioned, it can also be a demand response system at the same time. And you can actually produce a lot of it in the summer, store it in the natural gas caverns that we have. That's integrating the wires and pipes. And so you can reduce the production in the winter, which actually works. which brings the demand down. That's what brings it down from this dotted forecast peak to the top of the red. And then if we do hybrid home heating devices, you can get rid of the red part, so your peak demand becomes there. And you end up with only a 5 to 6 peak difference between winter and summer. That is a manageable amount of items, and then the whole load gets smoothed out from the solar battery backups. So it changes the way the system behaves. That flattening of demand means you don't need to increase the local distribution company assets, because this can be dealt with within their existing capabilities. So free distribution costs till 2030. So why? So I'm going to just go over a few slides to just talk about the different features of the different energy supplies and the considerations that have to come into play. So the first thing, and this is the obvious one, the ISO put this chart out. This is solar. It shines in the winter shines in the summer more than in the winter. That's just what happens. That blue line's our demand. So solar is kind of a problem in terms of looking for it in this latitude of Ontario, in terms of trying to get it to solve our problem. It can't solve the winter thing. In the summer it can, but it can't solve it in the winter. Wind, we showed all that daily spiking that was on the previous chart. It also has a profile that it's on average lower in the summer. It still peaks in the summer, but on average lower in the summer, goes up in the fall, goes up in the spring, flattens out in the winter. Not ideally matched to this blue line, which is the demand. You could argue this could balance with that, but you still have this huge problem in the winter in terms of offsetting the two, right? So there's challenges in that Mother Nature is not delivering this kind of energy in a manner that we want to use it. And so that's where the whole concept of storage comes into play. We have storage that can help make solar useful. The wind problem on this scale is not yet solved, right? And the ideas people bandy about is, for example, compressed air storage, pumped water storage. There's all sorts of things that people are looking at, and we'll get to what does the scale mean in a second. So hydro's got a similar problem. Again, it's a Mother Nature thing. We've got lots of hydro capacity across the country. It is all north, mostly. The problem with hydro capacity, particularly in the north, is winter happens, and so the water doesn't really flow in the winter as much. It can flow a lot in the spring, and then it tapers off. And in order to make that water profile look like our demand, which is this red thing, you have to build dams. Quebec did it by building James Bay. To meet our 2030 targets, we need another James Bay. That's how much we need. So if you want to talk about pumped storage, okay, we need pumped storage that covers 13,000 square kilometers of land. Then we'll be there. It's big numbers. This is the essential challenge in terms of looking at all these options. Okay. Switching to the new ideas, I mentioned solar battery, and that's, you take the solar on the house, you plug in a battery, you let it get controlled by a local distribution company, so it can do the microgrid thing. And basically what the big advantage of that is you can use solar and battery to shave peaks. Why does that matter? That means you can get rid of your peaking gas plants, one. Two, if you shave the peak, you're going to inhibit the need to build a distribution network up, because you can shave the peak and keep it local, right? And so what this picture shows is, in July, when the sun shines, it will create this bandwidth of solar energy. The yellow part it would use directly. The orange would be plugged into a battery. The battery then discharge when the sun goes down to meet the demand profile that is typical of Ontario household, right? So in this way, you end up flattening from this thing down to this bottom the demand on the local distribution system. So you apply that on mass scale, and you're doing a lot of peak shaving that will flatten significantly the load. That can happen. The white line that we use as the target, by the way, is what our baseload system in Ontario can currently do, right? So we just said, well, how much solar do you need to bring it down to what Niagara Falls will do, for example? And so that's that idea. Integrating wires and pipes. The one thing I am showing here is they have hybrid systems where you have a heat pump, and then you can have a natural gas furnace combined with it. You turn on the gas. The thing about heat pumps is when it gets really cold, they don't work so well. And so you've got some challenges. And when they get really cold and not working so well, you're actually drawing a lot more electricity to make it do its thing. They become less efficient. So if you want to manage the whole thing effectively without, causing cost to the distribution system, stick it in natural gas. We already got the natural gas pipes. Use it sporadically to get rid of the peaks, and that's how you can get rid of that amount of electricity by doing the natural gas. The other thing it does is you'd have to install more devices to get rid of the emissions, which allows all this red stuff to get distributed throughout the year, which has another effect of flattening the demand load on the system, which impacts on how much capacity you have to have in your system. So there's a number of electricity system savings that occur by doing those hybrids. Hydrogen, I'm just going to say a couple things about it. It's good for a lot of things. This picture, courtesy of University of Waterloo's Chemical Engineering Department, has a number of ideas on it. You can use fuel cell. You can use it for fuel cells. You can use it to blend down natural gas. You can use it to displace fossil fuels that are currently used to do production. And it also provides an energy storage system if you pump it into our natural gas caverns. Currently, natural gas in Ontario, they fill it up all summer. The spring, the summer, and the fall, they fill up our caverns with natural gas, and then they pump it out in the winter to supply our needs. So just use hydrogen instead of natural gas, and you can get that seasonal benefit of production, which again smooths out the seasonal load profile. Nuclear, one of the little known facts, because people talk about nuclear is not very flexible. So this blue line again is the demand that we've in Ontario for the last 4 years, and the green is the production from our nuclear plants. So, and the reason that they can track this reasonably well is because nuclear plants have an annual maintenance cycle, and they just kind of figure out when they're going to turn each unit down, take it offline at the times of expected low demand. So they're doing, so that actually, they can actually manage that, and that well, right? So they've been doing. So we started looking at new capacities. If you brought nuclear in, you could apply the same logic, and you get this profile that can be optimized of the new nuclear that starts to reflect that winter peak that we showed about. So we got this baseload option that could supply that function and avoid a number of other costs associated with gas plants. So those are the big paradigms. So the very quick summary. We want to avoid $27 billion a year because that's the cost of doing all this. If we're smart about it with these different kinds of options, the hydrogen, the LDCs control, the low-cost electricity, the hybrid heating, we can get somewhere. We know we can achieve the electricity on time, and if people want to go mass stuff, the question that's going to become part of the dialogue will be, we need a lot of electricity. We have a lot of hydro. When do you think we'll flood 10,000 square kilometers of land in Ontario to build that hydro? I think it's going to be really hard to get the social acceptance on that problem. So we have a problem. It has to get dealt with. Right? So I think we're going to be looking at, do I want to flood? Do I hate nuclear more? Because will the storage for wind show up in 10 years? Big question. So these are going to be difficult social decisions that need to be made. So cap and trade will be costing us $2 billion a year after 2024 because we're not going to get the targets because we're not going to build the electricity in time. I mentioned 2024 because we have the Pickering nuclear reactor is going to turn off by then. So we're going to lose a lot of capacity. And as soon as that happens, we've got a tougher emissions challenge. But if we're smart, we can become an economic powerhouse. There you go, really fast. Okay. So, questions on any or all of it? I'm going to start at the back.
Thank you very much. Very nice presentation. Very good to see that overview. I would be interested in the numbers you put out. This 27 billion versus the 3 billion. There's one slide with your proposal versus the common approach. And I'd like to ask a little bit if you could give a little bit of a background what the proportions of these individual items are. So you're showing, for example, wind and hydrogen imports would be, and the other ones are on one side, and some other proposals. And kind of, no, the other one.
This one? Okay.
Yeah, this one. So your four circles on the left and on the
Right.
There will be a certain
Correct.
you can comment a bit more on.
Okay, so the assumptions that we used in creating this scenario are the assumptions that were provided by the ISO in their Ontario Planning Outlook that they published last September to inform Ontarians during the consultation for the long-term energy plan. So that was the scenario that they had mocked up. That's the electricity components that come out of it. And so basically what they had, I'm going to go from memory, but there was like, oh yeah, there it is, roughly 2,000 megawatts of, or 4,000 megawatts of hydro in 2 phases. They had 6,000 or 7,000 megawatts of wind plus another 4, so another 10,000 megawatts of wind. That's doubling what we expect to have by 2025. They want to double it again. And then they assumed, I think it was 6,000 megawatts of hydro from Quebec in the winter. So, and then the transmission to build all that and connect it all together. One of the things about the other option is there's no transmission costs to speak of because the assets already exist everywhere, right? Because unless you build a new dam, you don't need a new transmission system. Okay, so does that answer your question? So on this side of the fence, in terms of the supply mix, most of the supply is coming from the nuclear, because we contrived this scenario. And the reason we contrived this scenario that way is when we did the research on what do they expect costs of all these different supplies to be by 2030. So solar, wind, whatever those projected costs come down. The nuclear one came out to like $86 after you take the risk elements out. Which we can take the risk elements out, because if you're going to build 20, you might screw up on the first one, but you're not going to be screwing up on a 20th one. So that's how that, right? So we just built all nuclear, got rid of all the wind, let it retire, kept the solar because it's useful with batteries, and didn't rely on imports from Quebec. Used a natural gas system instead. So that's where the philosophies around this scenario, that got the cost down, because we were just trying to, is there something that would be cheaper than this? That was the question. So there's a scenario. Does that answer your question? Okay, next.
Again, to echo a great presentation. In your philosophy, how is conservation built into your math through technology and social change? So if you look at the OBC now and how we're increasing the efficiencies and how we're building more airtight, and therefore reducing leakage, we're going to be using a lot less gas, and we'll be shifting instead of a winter peak to more of a summer peak to supplant the electrical load.
Yeah. So on the efficiency side of the fence, because that's where conservation comes, conservation comes into a number of different things. One is reducing the load, right? So what does the forecast demand have to do? So we used the profile of demand that ISO used, right? And in that profile of demand, going to the future, absent climate change, they've already built in a bunch of assumptions around conservation.
On the electrical side?
On the electricity side.
What about on the gas side?
On the gas side, we did not dig into that. We dug into that in terms of the analogies. On the gas side, we looked at, so let's go back to the building. So when we start talking about building efficiency being improved, that has to do with heat loss. Yeah, so that's whether it's electrical or natural gas, doesn't really matter. The buildings are getting tighter. And what that came out to was 50% of the homes getting 33% more efficient. Half the province has got to get that much better. It felt like a big, scary target. So we felt that was a big enough assumption. That's the only way we dealt with conservation, right? Isn't the assumptions on. Did not go there. So that's another piece that we did not look at, right? On the basis that there were a lot of assumptions in the forecast demand that already had the conservation principles baked in. New conservation principles we didn't look at in this study. We just did it by going, well, let's just assume we'll do some magic. Right? Okay?
Just want a quick recap on, so you presented all these, we're looking at the different sources of energy, and how realistic is it, how realistic is the 2030 deadline? Like, if you presented graphs which show that it's almost physically impossible to reach that, and whether it's legislation or not, it seems like a plan set up for failure if you want to go to 2030, and it's just so difficult. Like, yeah, this is the exact slide I was thinking of.
Yeah.
So, I mean, what about pushing the deadline further than 2030? How set in stone is that date?
Right. So fact, can't do it. So that's a fact. Everyone, they can't meet our targets. It's just not humanly possible because you can't build the energy options in time. And that's understood. Well, it's understood by the analysis. This is the environmental commissioner came out with the same answer, said you're gonna miss your target by a whole whack with the plans that have been put forward, which include an electricity plan as well as a fuels study that had also gone on. So you can't do it. So they have two options. One, slip the targets, right? Buy some time. Because if they don't, the other option is continue to buy emission credits from other jurisdictions. The thing about the US and their ambitions to meet 2030 targets, if they get, once Trump moves on and they get you serious about it again, they've got an easy job for the first big chunk because they use a lot of coal and have for a long time. So it's really easy to get rid of coal and replace it with a natural gas plant. They're not hard to build up. And so they're going to have emission credits for quite some time. They're going to be beating their targets for quite some time. So we will be buying from them. And they've already forecast that it's $2 billion or $500 million a year by 2020 is what we will be spending on California credits already. And I forecast that to grow to $6 billion a year by 2030 because we're not going to hit the targets. Right?
So as a society, basically, though, there is no progress almost done if you're still buying credits from somewhere else. Your economy or your society is still producing that same CO2, so there is no shift almost towards a cleaner
So
society.
we're going to make progress. We're not going to make progress on the pace of the Paris objectives unless they change something, right? That's what the message in the story was. Is well, wait a minute. You got they got a legislative thing that's going to cost us money. They could change that, but they got to wrap their heads around what does that mean to the Paris commitments. It's you get it. It's complicated, right? There's a lot of levers, but we cannot meet our 2030 targets. This isn't going to happen.
So do you think it's like a good idea that Ontario linking its cap and trade program with California?
So my personal opinion is no. So my personal opinion is you want a mechanism for carbon price. You do, and you want it to be everywhere, ubiquitous. So the notion of having a bigger economy running to a carbon price is a great idea. The implementation of connecting up with a market like California, whose needs are extremely different than ours, whose challenges are extremely different to ours, when you're in an environment where you're not going to meet your own targets, you're just signing up to sending money with no benefit. We'll be paying innovators in California to do stuff which may or may not be helpful to us because their problem's different. So I think it's a bad plan from that perspective. It's just going to have money going in the wrong direction. With Quebec, we probably could beat Quebec because they've already electrified their heat, right? So we've got an easier problem than them, right? So.
More questions? Yep. Go ahead.
Just a small one, probably also interesting on the political side. You've been talking about transportation, and I'm no expert in transportation or that, but I felt like the assumptions and the requirements of these 35% in something like trucks, that also feels very ambitious to me,
Yeah.
That's probably also a big challenge. So
Yeah.
I was wondering about things like rail transport or other things, if they're part of the conversation or...
Yeah, so I mentioned that, so we did not look at rail and aircraft in this study. That's part of that other things that we didn't look at. When we consider how much of the problem that is, rail is this little sliver and aircraft's that larger sliver. So they're important, but as far as our emissions go, they're not like the big driver. In terms of addressing the rail problem, you've probably heard in the news, right, on the GO trains, right, they're talking about hydrogen trains, which is a great idea because there's a company in Ontario that's kind of building the stuff. They're selling it to Germany. That might be something that works out for Ontario in terms of a competitive advantage. So rail they can do that with. They can address it with hydrogen. For big ships and aircraft, that's a challenge. And the tractor trailers, right? The large.
Sorry, I was referring to conversion. See if you can do more popular routes, conversion from truck transportation to rail, more freight, or combinations.
Yeah. So my understanding that there is a study. I think it's the government of Quebec that's sponsoring it. to look at how to move shipment of goods through different mechanisms so that you can optimize. And one of them was rail, which is easier to electrify to get them off, to get the goods off the trucks, right? So people are looking at that stuff, right? Absolutely.
More questions?
I want to provoke a question. So I said a lot of stuff here. Some of it must be inconsistent with some of your views. So, like I said, nuclear. Anybody talk about nuclear? I said, get rid of the wind. Anybody want to talk about that? Yeah.
Mark, usually I can share something with you, and if you want to answer this, some of the colleagues are of the view that if the number of electric cars on the road goes up, then we need more EV charging stations to be deployed, which means that the electricity generation from natural gas, which is currently at 9%, will go up. So the electric car is not that green. So that's an argument.
Right.
What are your thoughts about this?
Okay. So let's put the framework of, so electric vehicles. One of the things about electric vehicles that people are going, right now, it's a great idea, go out and get one, charge it at night, you can use clean electricity, then it makes sense. Okay. And that is true, right? Because we got a surplus of electricity at night. In the near term, it's a great policy to try and use our excess electricity at night to help charge electric vehicles. And hopefully between now and 2024, the remote control of the charging gets aligned with consumer behaviors, and we can have a systemic mechanism for charging vehicles at night. Now if there's too many of them, then you end up with a nighttime peak instead of a daytime peak, and you have the same problem. When 2024 rolls around and the Pickering nuclear plant turns off, that's 3,000 megawatts, which is 20% of our electricity production in baseload. That'll disappear, and at the moment, there's no replacement. The only replacement is natural gas. That's what's there. So come 2024, all those electric vehicles that were just added to the system will be powered with natural gas, and you're losing the benefit of electrification. One of the things about electric vehicles in the States that always amazes me is they are of absolutely no benefit in most states, because most states produce more emissions in making electricity than the car would. So the electric vehicle shift needs to be paired with the electricity system cleanup, otherwise you're not achieving emission reductions. Right? There's other reasons to buy electric cars, because you just want to. But from an emission reduction perspective, and the subsidies that we're putting on it from our carbon pricing, there's a mismatch until they align it. And that's the way it is. Right?
I understand. Thank you.
Yeah.
More questions? Yeah.
Would you pick power to gas over, investing in power to gas over investing in electric vehicle infrastructure in the short term?
I don't think those are choices people have to make. I think of all the technologies we looked at, you need to do all of them. And the power to gas notion is a mechanism by which, the power to gas is a couple of different notions. One is make a hydrogen whenever you want to make it, so you can optimize when it's made with regards to the electricity system, and then use it to fuel cars, right? The other is to blend in to the natural gas system and use it to heat homes in the winter. So as soon as you start talking heating homes in the winter with power to gas, you're not talking about electric car trade-offs or anything like that, right? For the hydrogen fuel cell versus battery electric cars, there is a trade-off, and that trade-off was, I thought, brought out relatively well by that chart from Toyota that says, depending on how far you want to go and how big your application is, fuel cells might be what you want to consider. At the moment, I will not buy an electric vehicle because I have a cottage and it's 300 kilometers away and there's nothing there, so I need a 600-kilometer range. So when they make one, I'll get one. Until then, I might get a hybrid because they're a good idea. Or I might get a fuel cell vehicle because, but they don't have the range yet either. So, those are the consumer behaviors that, impact on these things. Yeah.
What about the opportunities with RNG?
A renewable natural gas. So the
Waste incineration.
Waste incineration to produce electricity.
Produce the hydrogen,
Right. So in terms of extracting hydrogen from methane, whether it's natural gas methane or taken from a landfill site or whatever, if you're extracting hydrogen from it, you're still producing the CO2 from it, right? It's also an expensive process because you have to throw electricity into the mix to make the hydrogen, which then you're going to use. So we looked at that lightly, and we only looked at it lightly because it became very apparent very quickly. It was really expensive, not ready for prime time. So for our costing assumptions on what could be done by 2030, it didn't make the cut. Now, there's a couple things around that, which I'll get into. I got that slide on. So here we looked at getting all the methane out of landfills. That's what all this stuff was about. And if you just capture the methane, that's this little blue, the little green at the bottom, because the methane's coming out of landfills. And capturing that methane and not releasing it, if you just burn it, is better than letting it into the atmosphere. And just capturing it for whatever purpose you want to use it for would cost only this much, like in the carbon price. To convert that into methane that you can pump into the natural gas system, that's the renewable natural gas option from landfills, it costs a little bit more. There's other things that you have to do to do it. Large landfills, great idea. As soon as you get into the small landfills, and there's a lot more of these than there is of those, it becomes very expensive to use that renewable natural gas. There's also the synthetic gas, which has that whole methanation process of taking hydrogen, combining it with carbon dioxide, and then producing artificial methane. And again, that seems like a backwards kind of process because you got to get the hydrogen in the first place. So why don't you just stick with the hydrogen? So there's a number of funny things, and those haven't been costed out in any meaningful way by anybody yet either. So and that's where that magic comes in, because those are all good ideas. We didn't use them because we couldn't get cost data in our study. It wasn't a judgment. It was got no data, so we didn't use them. Okay. Fair?
Without opening, without opening the debate around nuclear, but you were mentioning low-cost nuclear.
Mm-hmm.
And when you look in the world, I think there's nuclear technology is a little bit in an up and down over the last time.
Mm-hmm.
Westinghouse is trouble. I think European reactors are going up in price significantly. I think the CANDU technologies, I'm not sure how the future is in the sense of there hasn't been much activity, I think.
Right.
So what's the uncertainty, or what's the certainty that the price will behave as expected?
Right. So these are all forecasts, right? So what's going to be the cost of battery storage? We had the same kind of questions around that. So what's the baseline that we used? The baseline that we used was the U.S. forecast for the cost of nuclear, and of course that did not in 2025 or whatever, plants that would be built a long time from now. In the face of that, yes, Westinghouse, poured the concrete wrong and went bankrupt. Areva in Finland poured the concrete wrong, and they're getting all messed up right now. So they're at risk. And those are real. It's funny how, so we look at large-scale projects and risk on them, because everyone talks about nuclear risks and overruns. It is about the concrete. And when you look at what other big energy infrastructure requires a lot of concrete, it's hydro. Okay, hydro, Muskrat Falls, dam, Site C in British Columbia, the dam in Manitoba. All of these things are double their cost. I made that up. Big, huge overruns on all of these guys. Why? Because it's really hard to pour concrete. I don't know why. Did a study. There's a couple of studies out there. As soon as you get to a large project, a large infrastructure project of any kind, anywhere on the planet, that involves a lot of concrete, cost overruns. Sky Dome, 407, pick it. Olympics, pick it. Doesn't matter. Big projects, human beings have difficulty bringing them in under cost. Right? The biggest, over the last 70 years, when you look at the stats, the one category of infrastructure that had the highest overall average overruns was hydro dams. So those are all good questions. So we use that U.S. forecast for electricity. The momentum around the planet around small modular nuclear reactors is looking at prices that are half that, like in the $60 per megawatt range. Full up base load, don't need anything else. There's like 90 companies out there investing in it. We did not use those costs in this study because didn't know about it then, but there's a lot of activity trying to hit that price point. And the reason they're coming in cheaper is they want to modularize the thing to get rid of the concrete. Go figure. There you go. Right?
So Mark, I guess we have one more question.
Yeah.
Like you say, like in terms of transportation, there will be a shortage of electricity in 2040.
In 2024 in Ontario, yeah, we're turning off a nuclear plant, 6 nuclear plants.
Question, like, is there any consideration of to meet that short-term target, transformation of the vehicle to LNG or LPG in Ontario?
Okay, so there's a lot of talk around natural gas vehicles, particularly for trucks, and the Natural Gas Vehicle Association of Ontario is lobbying. I do believe that the provincial government is allocating funding for those kind of notions because natural gas as a bridge is helpful, and natural gas trucks are better than diesel trucks, and they can build them. It costs a little bit more. You know, we've got the price for that. And so they should be pursuing it, and you know, people are pushing for that, for their own businesses to do that. So those are all good ideas. But even if you replace the entire fleet with natural gas, you don't meet targets. So it's not the answer, right? But it can get you somewhere, right? What's that? Yeah.
It's for the only for trucks, right?
Pardon me?
It's only for the trucks.
No, they're talking about cars and trucks and boats and ships and not planes, but yeah, there's a lot of options for natural gas, and they're all legitimate, and they all have a role, and they all have a benefit. You add them all up, they don't. If they're the only thing we do, we don't get the targets. So we need them because they're good. They can happen fast, right? And for trucking, there's not too many options.
So Mark, is it correct to say that after 2024, we will be using more natural gas for electricity generation rather than optimizing other sources of generation?
I don't know about the rather optimizing. We're waiting for the long-term energy plan to answer that question. But at the moment, there will be more natural gas used.
More natural gas.
Yeah, it's a given, right? Absent something we haven't heard of yet.
Sure.
Yeah.
We have one more question. Go ahead.
So now, given that those 6 plants are shutting down, your opinion, what is the province going in the right direction when it comes to the supply mix and the way its technologies is developed? Like, if you have a say if you were to be given a chance to have an ideal way of moving the energy supply somewhere, what would you do to?
Okay, so on the supply mix side, because I've come out with a lot of negative things around wind and solar. Wind and solar have a place. The mistake that Ontario did is they bet the farm on too much of it too soon, which is why we have too much of it right now, right? So that's first comment. In terms of going forward, the notion of solar with battery in the microgrids to level the peak out of the system so we can get rid of the gas plants, allow for that peak load serving to smooth out the electric charging, all that. Brilliant idea. They're working on it. There's a number of LDCs that are putting these things forward. That's where the idea came from. That's a great idea, and they should do that. But it's about integrating with storage. And the question on the economics is how quickly will storage costs come down, because they got to come down a lot. The forecast we used was based out of Massachusetts, where they forecast the cost of energy storage in around early 2020s. And combined with the solar price that was forecasted for that time, putting that together, that peak electricity was going to cost $130 a megawatt hour combined. And compared to a gas plant, when you look at the full cost, it's cheaper than a peaking gas plant. So that is already a good idea. So they should be doing that. However, it's going to take some time to get it right and to deploy it. The scenario we ran, where we went, if we can do this nuclear thing, you can get rid of the wind, get rid of the imports and transmission with Quebec. It's got a lot of economics, and they appeal to it. So we should be marching down that path. I personally don't see how we can achieve global emissions without nuclear energy taking a role. And it'll only take a role if people can make it safe, cheap, and can locate it and reliable and all those things that have to be done. But you only get to a place like that when you start throwing some money at it, right? So you should be investing in it. Whether you should bet the whole farm on it like we did with wind, I would say no, because you should never do that until you know what you're doing. But, you know, that's kind of where, you know, my bias would be is, okay, keep your eyes open and invest in hydrogen, invest in nuclear, invest in natural gas. You know, spread it around, keep an eye on it. Right? Yeah.
Going up with the consumption of natural gas on the called medium term. Every project comes with certain inertia. It takes time to do it, it takes time to implement it, it takes time for society as a whole, as individuals to wrap their head around it, to use it, pay it off, and then move on to something else. So when we go past 2030, based on projections that you've made, do you believe that we will create a lot of inertia around the integration of natural gas systems that will hinder us from going further towards 80% later on, towards I think it was 2050, when we may have to think about natural gas as a significant component as well?
Yeah. So how long before you don't need the natural gas system, right? The thing that came into my mind, Energy East, it's got canned, right? And for the last year after Paris came out, I've been wondering to myself, why build it? Because it's got a limited life. And can you build a pipeline and make it economic in 20 years where you're not going to have full capacity? So if you believe Paris, I was surprised that they kept pushing that Energy East thing. In Ontario, we've got existing natural gas infrastructure. It's there. Why they're expanding it to other communities is a good question, because they might get stranded. On the other hand, in order to protect those peaks and use it and integrate the natural gas system with electricity to avoid building the electricity infrastructure, maybe it's a good idea to have everybody access to a little bit of gas, right? So that's those little trade-offs. On the broader picture, 2030 targets, right? The energy, we came up with is you need this much. There's a curve here. 2050 is twice as hard, okay? And it's only 20 years later. That's up here. So right? So if you think about 2050, it's doing this, right? There's a big challenge out past 2030 to get to 2050. So the issues and the what are our mechanisms going to be, and what is the role of all the different options? It's only going to get more complex once you buy into trying to get rid of the emissions. Right? In Ontario, the issue is the heating is the tough one. Trucks is a global issue. Heating's an Ontario issue. It's not a Quebec issue.
So shouldn't we be planning for 2050?
I think so. You got to be thinking about that, because the assets are 30, 40-year assets, right? When you're building large-scale electricity, right? So, but that's beyond the view of governments, right? They have a shorter-term view on life, right? So, don't know what's going on with that. Now, to their credit, City of Toronto has their 2040 vision, right? So they've thought out that far. Right?
So I guess if we have no more questions, but I'm going to assure you that Marc will be here for the next 10-12 minutes, so you can talk to him on a face-to-face basis. Other than that, on behalf of University of Waterloo, Marc and Waterloo Institute for Sustainable Energy, we would like to thank you for your time and sharing some wonderful insights with us. Thank you so much.
You're very welcome.